Welcome back to the deep dive. Today we are strapping on the scuba gear and descending into what might be the most consequential open source breakthrough in AI this year. We are moving past the era of, simple fact-checking chatbots. We are entering the age of sophisticated AI researchers.
That's absolutely right. I mean, for years, the ability for an AI to truly plan and execute and then attribute complex, long-form research. Essentially write a well-cited paper that was confined to the largest closed proprietary systems.
Right. The big guys.
The big guys, exactly.
Yeah.
But our sources today, they center on a game-changing model called DR Tulu-8B, and that stands for DeepResearchBench.
And our mission for this deep dive is, I think, critical. We are not just celebrating a new benchmark score here. We're going to dissect the foundational technology that makes this all possible. We really need to understand the core, just the brutal challenge of teaching an AI to do complex research.
And all the pieces that go with it. The planning, the iterative searching, the synthesis.
And then mastering that necessary skill of rock-solid attribution. That's the holy grail, isn't it?
It really is. And we'll be spending a lot of time on the novel training technique that allowed this, relatively small 8 billion parameter model to compete with the giants. That technique is reinforcement learning with evolving rubrics, or RLER. If you want to know how to train a small model to punch way, way above its weight class in cognitive complexity and trustworthiness, RLER is the crucial piece of the puzzle.
Okay, so let's start by leveling the playing field with a core definition. When we talk about these deep research or DR models, what kind of cognitive workload are we actually demanding from the AI?
Well, a DR model have to perform a multi-step research workflow. This is just fundamentally different from a single-turn question-answering system. It starts with complex planning, deciding what information is even needed.
So it's not just answering, it's asking its own questions first.
Precisely. Then it moves through iterative searching, potentially using, multiple specialized tools like the web, academic papers, maybe proprietary databases. And finally, and this is the hard part, it demands sophisticated synthesis of all that information into a long-form, well-attributed report that answers a complex, often ambiguous question.
So it sounds less like asking, who won the World Series in 1985, and much more like asking, analyze the current regulatory landscape for lithium-ion battery recycling in the EU, and compare the narrow and broad approaches in terms of environmental impact and projected supply chain stability.
That's a perfect illustration. The second question, it requires comparing disparate concepts, projecting future outcomes, and citing specific directives or policy papers. It's a task that would take a human researcher hours, if not days, and it requires a mastery of citation standards.
And the model we're focusing on today, DR Tulu-8B, is specifically the first open model designed from the ground up to tackle this level of open-ended long-form complexity.
Yes, and the results are genuinely startling, especially given its small size. I mean, we are talking about a model that substantially outperforms all existing open deep research models, sometimes by margins exceeding 40 percentage points across key long-form benchmarks like ScholarQA-CSv2 and HealthBench.
Wow, 40 points is not a small margin.
It's a blowout.
But here's where it gets really interesting, and this addresses that proprietary gap we talked about. DR Tulu-8B doesn't just beat the open models. The sources indicate it matches or even exceeds proprietary closed systems. Systems like the high-tier research functionalities offered by OpenAI Deep Research and Perplexity Deep Research on the majority of these benchmarks.
It just redefines the efficiency frontier. It demonstrates that the key to advanced research capability is not sheer scale. You don't need a trillion parameter model. It's about a highly effective, specialized training methodology that teaches the model how to use its tools and structure its knowledge.
So it's not about being bigger, it's about being smarter in how you learn.
Exactly. Brains over brawn, in a sense.
Yeah. All right, so if complex research is the goal, why has this remained such an uncrackable problem for open source AI until now? What was the fundamental limitation in the old training methodologies?
The foundational issue is the reward signal.
Yeah.
I mean, how do you accurately score the quality of a complex, multi-paragraph report? Most existing open models, they rely on reinforcement learning with verifiable rewards, or RLVR.
Right, and RLVR is great for simple, objective tasks. If the model answers 2 + 2 = 5, the reward is 0. If it answers 4, the reward is 1. It's binary, it's simple.
Exactly. It's clean.
Yeah.
But open-ended deep research is knowledge-intensive and, subjectively judged on multiple dimensions. Previous open models failed because they were trying to use these short-form QA tasks, which have simple rewards, as a proxy for training complex research skills.
A proxy that just wasn't good enough.
Not even close. That proxy fails spectacularly when the model has to plan and execute a comprehensive long-form report that may not have a single right answer.
I get the ambiguity problem. I mean, if I ask a human researcher to write a report on the economic impact of carbon capture technologies, the criteria for good are just. They're all over the place. Completeness, timeliness, the synthesis, source quality. It's a massive evaluation burden.
It is. And as researchers like Zood and others highlighted back in 2023, the criteria for a good long-form response are often underspecified and highly compositional. A reward model has to somehow simultaneously evaluate the truthfulness of individual claims, the coherence of the whole argument, the appropriate use of external evidence, and the citation format, all at once.
And this leads directly to the knowledge gap problem, doesn't it? If your evaluation itself is static, it can't evaluate dynamic, real-world knowledge that the model might discover during its search.
Precisely. If I train an AI using a static judge, that judge only knows what it learned up to its cutoff date. Reliable evaluation requires access to a vast, dynamic corpus of world knowledge. So if the AI policy model finds a cutting-edge paper published yesterday, but the static judge wasn't trained on it,
the judge has no idea if it's right or wrong. It can't reward the AI for citing it.
It can't possibly reward the AI for citing or synthesizing that new evidence accurately. This means the judge is constrained by the model's static parametric knowledge, and that's just insufficient for knowledge-intensive DR tasks.
Okay, let's break down the two failed static approaches detailed in the sources. First, the simplest failure mode, general rubrics.
General rubrics, right. So this is using one single broad rubric across all tasks. Criteria like the response should be comprehensive and well-cited. This approach, as proven by Gunjal and his team in 2025, leads to catastrophic failure through reward hacking.
Tell us what reward hacking actually looks like in practice for a research agent. What's the model doing?
It's optimization theater. That's a great way to put it. Since the rubric is too general, the model learns to exploit the biases of the reward function rather than achieving true quality. For example, if the reward function scores length highly and citation quantity highly, the model might produce an extremely verbose, rambling report.
Just filler text.
All filler. And then it appends 30 citations, half of which are irrelevant or only tangentially related to the actual claims, just to boost the metric score. It's optimizing for the proxy, the length and citation count, instead of the genuine goal of accuracy and synthesis.
So they write a paper that looks cited, but if you actually check the sources, it all just falls apart.
It's an illusion of research.
Okay, so that's general rubrics. The second common approach was closed book rubrics. How is that different?
So closed book rubrics, they try to be more specific. They're generated by an LLM for a specific question, but critically, they are created without performing a search. The generating LM is operating, well, closed book.
And that brings us right back to the static knowledge problem. If I ask a question about a newly emerging regulatory framework, the closed book rubric generator it won't know the answer. It can't.
Exactly. The constraint is the generating LM's static parametric knowledge. If the task is about synthesizing evidence that requires accessing external dynamic sources, like a new clinical trial result or a new political policy, the closed-book rubric cannot anticipate, evaluate, or demand the inclusion of that critical external evidence.
So the rubrics end up being really vague.
Incredibly vague and descriptive. Things like the response should discuss the pros and cons. They're not assertive and specific. Like the response must mention the limitations outlined in Section 3 of the EU directive. This inability to engage with dynamic knowledge is why the DR Tulu researchers had to fundamentally rethink the entire reward loop.
So if static evaluation fails because the world of knowledge is dynamic, the solution has to be dynamic evaluation. And this brings us to reinforcement learning with evolving rubrics, or RLER. How does RLER fundamentally change the reward dynamic?
I think I need an analogy here to really grasp the novelty. Okay, think of RLER as moving from a fixed, standardized test, that's your static rubric, to hiring a highly adaptive, personalized research coach. This coach, unlike the fixed test, watches you perform, sees your mistakes, identifies new facts you discover, and then instantly updates its evaluation criteria for your next attempt.
Oh, I like that. So the rubrics are constructed and maintained to co-evolve with the policy model during training?
Precisely. Instead of grading the model against a fixed precompiled checklist, RLER provides discriminative on-policy feedback that is grounded in the real-world knowledge that the model itself discovers through search. This constant adaptation ensures the training signal stays relevant, specific, and not exploitable.
Let's trace this mechanism using the detailed flow provided in the sources. How does the rubric generator, how does it actually synthesize these dynamic criteria?
The process starts iteratively. So at each training step, the policy LM generates multiple rollouts. A rollout is a complete research attempt. The initial plan, the sequence of tool calls, the retrieved documents, the whole search trace, and then the final synthesized response.
Okay, so it does a bunch of tries.
Right. And the DeepResearch LM is then fed these rollouts, specifically contrasting the outputs of the high-quality rollouts with the low-quality rollouts.
So the quality difference between attempts actually informs the new rubric.
Exactly. It's using contrastive learning. By observing a rollout that was successful, say it found a new fact and cited it correctly, and a rollout that failed, maybe it reward hacked the citation count. DRUBRIC creates new rubrics that specifically capture the distinguishing features between the good and the bad.
And because those rollouts have the search traces, the actual documents, the rubrics are grounded in reality.
That's the key. The rubrics dynamically incorporate that newly explored external information.
That's how they solve the knowledge gap. The evaluation criteria are always up to date with whatever external information the model is currently interacting with. So what are the specific types of evolving rubrics they generate?
There are two crucial types. First, you have positive rubrics. These capture strengths or new, relevant knowledge that the current policy model explored that wasn't covered in the original initial rubric set. These reward exploratory success, finding new, valuable, and necessary information.
So if the model discovers an unexpected but highly relevant side effect of a policy, the positive rubric rewards it for that discovery in subsequent runs.
Absolutely. Then the flip side is negative rubrics, and these are vital for closing down those unexpected failure modes and summarizing undesirable behaviors. They penalize specific reward hacking strategies, like copying retrieved results verbatim to maximize citation precision, or, more simply, writing overly long, irrelevant filler text just to boost the length metric.
The sources gave a fantastic anecdote about the base model's unexpected behavior that RLER was able to quickly correct. Tell us about the Python code problem.
This is a perfect demonstration of the system's adaptiveness. During early rollouts, the base Quinn model, which wasn't specifically instruction-tuned for this, sometimes unexpectedly produced snippets of Python code inside its research reports, which obviously a research report shouldn't contain stray code.
And a standard static rubric might not even think to check for Python code because it's such an irrelevant, emergent behavior.
Exactly. A closed-book rubric would completely miss it. But the evolving rubrics identify this undesirable behavior as it emerged across the rollouts, and it created a specific negative rubric against it. The training adapted, and the use of RLER led to a measurable reduction in code-containing responses over the training period. This shows RLER doesn't just grade existing criteria, it proactively identifies and corrects the model's specific, unique flaws in real time.
That efficiency is just staggering. Now let's talk hard data on quality. Table 1 in the source compares the quality of the feedback. The sources focus on the fraction of assertive claims. Can you define the difference between assertive and descriptive for us? Because that seems key.
This distinction is paramount for training quality. So a descriptive claim is vague and easy to satisfy. Something like, the response should discuss global market trends. This leads to superficial answers.
Right, you could write anything for that.
You could. But an assertive claim is specific, concrete, and requires verifiable content. For example, the response must mention the Q3 2024 earnings of specific companies X and Y and cite the accompanying press release.
So descriptive rubrics invite low-effort answers, while assertive rubrics force the model to perform difficult, verifiable synthesis.
Precisely. And the data shows that closed-book rubrics are inherently limited, with only about 22% of their claims being assertive. They're vague because they can't know what external facts exist. However, the search-based rubrics, both the initial set derived from the environment and the continually evolving set, are dramatically superior, with over 50% of their claims being assertive. This gap is the efficiency game. The rubrics are grounded in external facts, so they're forced to be specific about what must be included.
If you're using a closed-book rubric, you're training a model to hit the broad strokes. If you're using RLER, you're training it to hit verifiable facts.
That's the core difference in training philosophy right there.
But if they're constantly adding rubrics based on every batch, how do they manage the complexity and the evaluation costs? You can't just let the rubrics set balloon indefinitely. That would be computationally insane.
Right, it would. And that's handled by a sophisticated two-step rubric buffer management and filtering mechanism. First, they filter out any rubrics with 0 variance in their reward scores.
Why 0 variance? What does that mean?
It means that a rubric with 0 variance, well, all the rollouts either satisfy it perfectly or they fail it equally. So if it can't differentiate between a good output and a bad output, it provides no discriminative value for the training update. It's just dead weight.
Got it. It's not helping the model learn.
Not at all. Yeah. So after removing the non-discriminative ones, they compute the standard deviation for the remaining rubrics. That's the measure of how much a rubric varies in its reward across the batch. And they only retain the top COMAX rubrics with the highest standard deviation.
So they are actively pruning the rubrics that stop providing useful feedback or become too easy. This ensures the focus remains on the most challenging, most informative criteria for improvement.
It keeps the training signal sharp and focused. And beyond RLER, the sources mentioned that auxiliary rewards were necessary for structural compliance, even if they were given small weights.
What kind of structural elements do they need to encourage?
Well, they needed to ensure the model learned the language of being an agent. These auxiliary rewards included format rewards, which ensure the model correctly uses its internal tools and output structure like putting the final synthesis inside the answer tags. And critically, citation rewards. These heavily encourage the wrapping of claims in that specific cite EAD format, linking the claim back to the source identifier retrieved during the search trace. These rewards ensure the mechanical correctness, while RLER focuses on the semantic quality of the research.
Okay, so RLER is the brain, but it needs a body, the infrastructure, and the training regimen to function. Let's move into the two-phase training process for DR Tulu, starting with phase 1, supervised fine-tuning, or SFT.
Right, so phase 1 is the cold start solution. You can't just unleash RLER on a generic base model like Qwen3-8B. A base model is powerful, but it doesn't intrinsically know how to plan multi-step research or parse complex user queries into tool arguments, or crucially, interact with those citation XML tags correctly.
So SFT is about teaching it the procedural grammar of being an agent, giving it the basic vocabulary.
Precisely. They fine-tuned the model on high-quality, teacher-generated trajectories. These are full demonstrations, a perfect example of a human or a powerful teacher model like GPT-5 performing the research workflow. And that includes the explicit think steps, the multi-tool calls, and the flawlessly cited final output. This gives the model the necessary behavioral scaffolding,
The basics.
the basic planning, tool use skills, and the necessary citation format competence, so that when RLER starts, the model is already capable of meaningful exploration instead of just flailing around.
And the data mix for SFT was key here. The sources say they used a blend of long-form and short-form data. Why was that modest inclusion of short-form data so important?
This was a critical ablation insight highlighted in Figure 6 of the paper. The SFT data included the complex open-ended queries from sources like SearchArena and OpenScholar, but they mixed in concise, verifiable QA data from Hotpot QA and TaskCraft. If they relied only on the long-form data, the model became excellent at synthesis, but sometimes lost its ability to be concise and accurate for simpler questions.
So got too long-winded.
Exactly. But conversely, if they relied too much on short-form data, the model struggled to synthesize longer reports. It often resulted in structural collapse when faced with a complex task.
So the balance allows DR Tulu to maintain general-purpose competency, the ability to provide a concise, high-precision answer without sacrificing its superior long-form research performance.
It's a very pragmatic approach. You want the model to be adaptable enough to handle both a simple factual query and a comprehensive market analysis. The SFT mix ensures that versatility.
Okay, so once SFT is complete, the model moves to phase 2. Online reinforcement learning with RLER, they used a customized GRPO method. Can you quickly clarify what that is for us?
Sure. GRPO stands for Generalized Proximal Policy Optimization. It's a standard, stable RL algorithm. In this context, online means the model is iteratively generating rollouts using real tool calls in the environment. It's not using pre-cached data. The model is learning by doing and then scoring the final answer against those dynamic evolving rubrics we just discussed.
Now, let's tackle what seems like the biggest infrastructure challenge in online training: time and cost. Especially when you're dealing with external tools like search APIs, latency must kill training efficiency. So how did they achieve that crucial efficiency detail? Asynchronous tool calling.
This is perhaps the most underrated yet vital innovation in their entire infrastructure. Think of the traditional synchronous model like a restaurant chef. They take an order, which is a tool call, they stop all other cooking, they wait for the waiter to bring the ingredients, the API response, and only then do they start the next dish.
Which means there's a massive amount of idle time. The GPU is just sitting there.
Exactly. With asynchronous tool calling, which they implemented via their Model Context Protocol, or MCP, the moment the model triggers a search request, say, a web browse, that request is immediately sent out. And crucially, the inference engine doesn't wait. It puts that specific generation request to sleep and instantly pivots to generating the next policy rollout in the batch.
So the system is concurrently managing dozens of search requests and generation requests all at the same time.
Yes. While rollout A is waiting 500 milliseconds for Google search, the system is busy generating rollout B, C, and D. Once the results for A come back, the system wakes up rollout A's thread and feeds the information back in. This tight concurrent control over tool calls avoids blocking the inference loop, it effectively manages API rate limits, and it dramatically reduces the wall clock time required for training. It makes the whole online RL process feasible and affordable.
That's just phenomenal engineering, and this is all unified under the custom agent infrastructure they open sourced, the DreAgentLib.
Yes, DreAgentLib provides that unified backend for multi-tool search. It supports 3 specialized tools that are crucial for deep research. You have Google Search for broad general web snippets. Then there's Web Browse for crawling full pages when you need deeper context. And Paper Search, which is specifically integrated with the Semantic Scholar API for accessing academic literature.
We should probably formalize the action tokens here as they really define the model's agency. What is the detailed tool usage protocol?
The protocol is governed by 3 key action tokens the model has to learn to employ. First, think, where the LM explicitly externalizes its reasoning. It plans the next search step or synthesis step. Second is call tool, which invokes one of the 3 specialized search tools, and it can specify constraints like a query string or a date range. And third is answer, which produces the final synthesized response and terminates the agentic workflow.
And the attribution requirement is a hard and fast rule at that answer stage.
Absolutely. This is the cornerstone of a DR model. The requirement is that any factual claim in the final answer must be enclosed in those cite-id tags, linking back precisely to supporting source identifiers from the context retrieved by the tools. And RLER ensures the model not only performs the research, but rigorously adheres to this standard of verifiable attribution.
All right, so all this engineering and this RLER innovation, it all culminates in the performance data. This is where the rubber meets the road. Let's start with how DR Tulu stacks up against its open source competitors.
Table 2 provides the evidence, and it's pretty clear-cut. DR Tulu-8B consistently and substantially outperforms every existing open deep research model. We're talking about models like ASearcher and WebThinker. It beats them across all 4 long-form benchmarks: ScholarQA-CSv2, HealthBench, ResearchQA, and DRB.
You mentioned before that the failure margins of the prior models were sometimes 40 points or more. Why was the gap so huge?
Well, it goes right back to what we were talking about in Section 1. Those prior open models were often trained solely on short-form QA, on RLVR, which means they were never incentivized to learn the complex structure and attribution required for long-form reports. So when they're faced with a benchmark that penalizes a lack of synthesis or, critically, lack of citations, their performance just collapses.
So they might get the facts right, but they fail the procedural test of being a verifiable research agent.
Exactly. Dargatulu, trained with RLER, masters both the content and the procedure.
But the real attention grabber here is the comparison to the proprietary giants. Matching or exceeding closed systems is a huge statement about the potential of specialized training.
It is transformative. DR Tulu-8B is competitive with systems like Perplexity Deep Research and Claude Sonnet Search. On ScholarQA-CSv2, which is a very difficult, knowledge-intensive benchmark, DR Tulu achieved 86.7 points. That's significantly higher than OpenAI Deep Research at 79.6 and Perplexity Deep Research at 67.3. This just demonstrates that for complex, attributable research, model scale is secondary to training effectiveness.
And this leads us to the cost advantage, the massive aha moment of this whole endeavor. I mean, if you have performance parity, but one system costs thousands of times more to run than the other, that changes the entire landscape.
The efficiency gain is staggering, and it has huge implications for the entire AI ecosystem. Researchers estimated that proprietary systems like OpenAI Deep Research cost approximately $1.80 per query on the ScholarQA-CSv2 benchmark. This cost is driven by the sheer size of the underlying models and the high volume of expensive synchronous API calls.
Okay, $1.80. What is the operational cost of DR Tulu?
In astonishing contrast, DR Tulu costs approximately 1/100,000th of a cent per query. That's USD 0.00008. Now, that figure excludes the cost of hosting the AB model itself, but it only factors in the external API calls required for the search tool usage.
Well, let me make sure I heard that right. That is an efficiency gain of over 20,000 times on API costs alone.
Yes. We are talking about orders of magnitude difference. And this doesn't just benefit big tech. This democratizes the ability to perform high-quality, large-scale, deep research.
Let's unpack that implication. For a startup trying to build a sophisticated knowledge engine, or for an academic research lab that needs to run tens of thousands of complex queries for a systematic review, $1.80 per query is prohibitive, it's a non-starter, but $0.000008 per query is accessible.
Absolutely. This fundamentally shifts the geopolitical and academic balance of power. Access to high-quality AI research capability moves from a privilege exclusive to those with massive compute budgets to a utility accessible to any lab, any student, or any institution globally. It proves that specialized, well-engineered open models can offer elite cognitive services at commodity prices.
Now, let's drill down on RLER's specific contribution. We know it works overall, but what specific performance gains did the RLER phase deliver over just the SFT-only model? Table 3 is instructive here, particularly around attribution.
Right. RLER training yielded specific, measurable gains exactly where it matters most: trustworthiness. The most notable improvements were in citation precision and citation recall on ScholarQA-CSv2, both improved by over 25 points after RLER training.
We need to translate that 25-point jump for the listener. What does a 25-point increase in citation precision actually look like for the end user?
It's the difference between a highly reliable scientific tool and a fluent BS generator. A massive gain in citation precision means the model is dramatically less likely to invent citations or claim a retrieved source supports the fact that it doesn't. A massive gain in recall means the model is much better at identifying every piece of evidence necessary for the synthesis and correctly citing it. This jump confirms RLER excels at addressing not just what the answer is, but where the answer came from.
And the gains in content quality coverage and comprehensiveness were also consistent, around 3 to 4 points, but the attribution gains were really the headline. It proves RLER is the key to training for verifiability.
It teaches the model to fear the error of misattribution more than the error of missing a detail.
Okay, moving to real-world impact. The model was tested on a challenging out-of-domain expert task: genetic disease QA. This is highly specialized medical genetics.
Yeah, this task requires assessing therapeutic eligibility for specific genetic variants, meaning the model has to synthesize sparse, technical information from specialized scientific databases and publications. It's a perfect high-stakes test for a DR system, because interpretability and evidence attribution are mandatory for medical decision-making. And the model was thrown into this domain without explicit RL training on this exact data.
So how did DR Tulu generalize to this specialized medical domain, a totally new field for it?
It generalized remarkably well, as shown in Figure 5. It outperformed the scientific literature synthesis specialist AI2 ScholarQA, which is itself a very capable system. And crucially, DR Tulu matched proprietary systems like GPT-5 with OpenAI search, especially on the metric of evidence synthesis.
Evidence synthesis, that sounds like the cognitive high ground. What does that metric measure specifically?
It measures the model's ability to describe the nuanced functional relationship between multiple sources. So it's not enough to just list source A and source B. The model must explain how source A's finding corroborates or maybe contradicts source B's finding to create a complete therapeutic recommendation. This success on evidence synthesis proves the quality of the learned agentic reasoning process that's imparted by RLER.
Finally, let's look at the adaptive tool and domain usage, demonstrated in figures 8 and 9. Does the model simply default to Google search for everything, or does it intelligently select the right tool for the job?
It is highly intelligent and adaptable. This model has learned to identify the type of knowledge required by the query. So for scientific benchmarks like ScholarQA-CSv2, the model relies overwhelmingly on paper search, 96.8% of tool calls.
It knows that for scientific facts, the web is often untrustworthy. You need to go directly to the academic source.
Exactly. But conversely, for general domain questions in the deep research bench, it correctly flips its preference. It relies heavily on Google search about 71.3% of the time and web browse. It has learned a cognitive model of information authority. And Figure 9 reinforces this by showing domain specificity. When it's tackling HealthBench, the model targets highly authoritative domains like cdc.gov and mayoclinic.org in its search calls. It's not just using the right tool, it's using the right tool to search the right digital address.
So we have an adaptable, efficient, verifiable, open source, deep research agent. Let's delve now into the broader implications and the remaining analytical challenges the researchers faced. First, the surprising finding on short-form generalization.
This was unexpected. Despite the RL phase being focused exclusively on optimizing complex long-form content using RLER, the final model, DR Tulu-8B, actually showed an average gain of 4.4 points on short-form verifiable QA benchmarks like Simple QA and 2Wiki.
So improving its ability to plan, synthesize, and cite a multi-paragraph report somehow also improved its fundamental ability to nail a concise fact. How do we explain that generalization? That seems counterintuitive.
The implication is that the RLER process, by forcing the policy to externalize and refine its reasoning, and by rigorously selecting optimal search paths, generally improves the model's internal coherence and reasoning capability. So when the model needs to answer a concise question, it now has a more robust, generalized ability to assess knowledge, even if it doesn't execute a full, multi-step plan. The long-form training acted as a general intelligence boost.
Now let's discuss what the sources called the mismatch challenge. This seems critical for understanding the limits of current RL systems. The sources noted that the models achieving the highest training reward didn't always achieve the highest final downstream evaluation performance.
This is a thorny problem that exists across much of reinforcement learning, especially for these open-ended tasks. It indicates that the training reward signal is not a perfect proxy for true, external, human-judged quality.
Right, so the in-loop judge for RLER was GPT 4.1-mini. If the model optimizes perfectly for that judge, but the final benchmark uses external expert rubrics, maybe from human scientists, they might disagree on what constitutes perfect quality.
Exactly. The discrepancy stems from potential reward hacking towards the specific preferences or biases of the training judge, GPT 4.1-mini. For instance, the judge might implicitly prioritize comprehensiveness over conciseness. This would lead the model to maximize training reward, but then when it's faced with an external expert who prioritizes precision and brevity, the model falls short on the downstream metric.
But if RLER is designed to fix reward hacking by creating these dynamic, specific negative rubrics, why does this mismatch still persist? Doesn't that suggest that even the RLER rubrics, while excellent, still don't perfectly capture the total complexity of human expert research standards?
That's the core tension. RLER significantly mitigates the issue compared to static methods, but it doesn't eliminate it completely. It confirms that the external, expert-crafted rubrics used in final evaluation are highly nuanced. They capture aspects like tone, narrative flow, or subtle evidentiary hierarchy that are incredibly difficult to codify into a simple, automated training reward signal. Perfect alignment remains an unsolved problem, which suggests a need for even more complex, adaptive human feedback loops in the future.
Let's pull all this knowledge synthesis together using the visualization concept from Figure 10 that captures RLER's value proposition from a cognitive perspective.
Okay, think of knowledge acquisition as mapping a territory. The innermost territory is the closed-book rubrics. They are limited strictly to the model's parametric knowledge, just what the model remembers. The next layer out is the knowledge territory incorporated by initial search-based rubrics. This immediately expands the evaluation criteria to include knowledge available through a current web search augmented search knowledge.
And RLER adds the final and most valuable layer to that map.
That is the knowledge captured by evolving rubrics. They fold in knowledge that is newly explored by the policy during specific training rollouts. This is knowledge that required complex planning, multiple tool calls, and high-stakes reasoning to uncover. This ensures the evaluation criteria evolve not just with the availability of data, but with the model's cognitive sophistication and exploratory success.
This concept fundamentally redefines how we scale the verifier then. Instead of just adding more processing power, you're adding contextual intelligence.
It's framed as providing a new dimension for scaling verifier compute. Traditionally, scaling the verifier just meant increasing the reasoning tokens available to the reward model, essentially giving it more time to think about a limited context. RLER changes the game by enriching the information available to the judge. By presenting the judge with the policy's reasoning process, the specific external knowledge grounding, and the contrastive examples of good and bad responses, RLER enables the reward model to use its fixed compute budget far more effectively and meaningfully.
This deep dive into DR Tulu-8B and the RLER mechanism has been incredibly illuminating. We've covered a major innovation in how AI is taught the skill of verifiable research, created a high-performing multi-tool agent, and witnessed a massive transformative cost efficiency achieved by the open source community.
DR Tulu-8B represents a monumental step forward for open source AI. It proves decisively that complex research, high attribution quality, and adaptability are not traits exclusive to proprietary multi-trillion parameter systems. By investing in dynamic training methods like RLER, researchers have provided an affordable, efficient, and transparent path toward developing highly reliable AI knowledge engines. The fact that an 8 billion parameter model can compete on evidence synthesis with the closed-source giants is truly a game-changer for accessibility.
It really raises the bar for every open model going forward. But let's leave our listener with one final provocative thought that emerges directly from the operational reality of relying on these tools.
DR Tulu's success is predicated on its ability to use tools like Google Search and Semantic Scholar, which means its knowledge is inherently tied to the state of the live internet environment. Our sources referenced a specific finding in Table 12, which studied the stability of search results. They found that if you issue the same query just 1 week apart, the results are surprisingly unstable. The overlap in the top 10 list is often only around 6 results, and the exact ranking changes significantly.
The web isn't an archive, it's a living, shifting entity. Sources are added, they're deleted, ranking algorithms are tweaked daily, and content is frequently updated.
Exactly. So the provocative question is this. If the underlying reference environment, the live internet, is inherently unstable and constantly shifting its consensus, what are the long-term implications for using these large language models as reliable scientific historians?
If the model provides a perfectly cited report today, but a critical piece of evidence it cited disappears or is deranked a week later, the report's verifiability is immediately compromised. It's not repeatable.
So does the inherent instability of the internet environment necessitate a fundamental shift in how we design and evaluate these research agents, perhaps requiring them to reference immutable data snapshots or archival versions of web pages rather than live search results? This is the tension. We want the system to be up to date, but we also demand that scientific knowledge be reproducible. The dynamism of the web is a practical challenge that researchers are only just beginning to confront.
A fascinating problem of engineering meeting epistemology. Thank you for guiding us through this incredibly deep dive.
My pleasure. Go forth and research.